Next slide, please. Okay, so this talk is about generating C. And I happened to observe a reaction of some people on the title of this talk and on this paper. And that complex reaction can be represented by one word. Next slide, please. Why? Oh, I mean, to be honest, this why on earth? Next slide, please. So why at all to write C by hand? So, well, C is, I mean, well-known and general-purpose language, and it has by now lots of tools and lots of IDEs and so forth. Then why, generating if you can write it by hand? Next slide, please. Second, if a higher language is desirable because C feels too low level, then nowadays there's many compilers that produce C or somewhat related to it, LLVM. Why not to use them? Next slide, please. Finally, why to even talk about it? Generating C is so trivial. Then what is the paper can be all about? Why is it to talk about? Next slide, please. So this talk is about is to answer these questions. So this would be the bulk of the talk, and the paper has more details and more examples, but I'll concentrate on this question. So the first is why to even generate C. So here is the example from basic linear algebra library, typical high performance code. Actually, this area, this research is all about is high performance code. Well, after all, if you are writing actually in C, then you're probably thinking about high performance, because if you don't, there are plenty of other languages to write code in. So that's one of the simplest example in basic linear algebra is adding two vectors. One of them is scaled by some factor alpha. And the code is called DuckSP. So AX plus P, AX plus Y, the XP. And D, it means double, it is double precision. It means 64-bit floats. So here is the straightforward C code, which is, very idiomatic, and it's very easy to write by hand. And it's clear what it does. Well, unfortunately, it is not fast code. Next slide, please. And here is the typical fast code, which is several times faster than the naive code. It is taken from OpenBLAS. It's a fragment. There is some epilogue and prologue, which it's allowed it to fit on the slide. So I have to apologize for the very simple example because, well, matrix multiplication would have been much interesting, but unfortunately that wouldn't fit on slide at all. So this fits barely. So the code we see is quite typical of high performance code. There is some long sequences of kind of assignments, and then there is another sequence of updates, and then there is some kind of update on the indexes and so forth. So why things are done this way? Well, the reason is to hide memory latency. Because nowadays, even a single core has enough resources to execute, to support, or try to execute several instructions in parallel. So, for example, here, when we get to M1, if we try to compute the value to assign to bind M1 to, so we need to fetch data from the vector x at index ix. Well, chances are this data isn't available in cache immediately, so it has to be fetched from memory, and memory takes time. So the CPU looks on the next instruction, and it also fetches from memory, but from a different address. And it doesn't seem to be needed any of the data from the previous instruction. So it can be tried while the first instructions is where the memory is reading the data, and again from the third and fourth and so forth. Now we come to the line where it says Y to update location Y. Hopefully, by the time computer fetch from X is finished and multiplication can be completed, and M1 actually has the value. So now we can update Y. Well, of course, updating Y also requires reading and writing, so it takes time, and CPU can look at the next instruction and next instruction, and so can execute this in parallel. So that's the reason for this complicated code. Why there is a, I wrote, unrolled this loop 4 times. So there is M1, M2, M3, M4, and 5 on 8. Well, that depends on memory organization, on the speed of the buses, on how many resources CPU has to manage to keep track of instructions in parallel, and many of these parameters. And most of the parameters actually aren't even publicly disclosed. So it's not easy, it's not even possible to compute how many times you need to unroll the loop. Why 4 instead of 5? So how do the people do that? It's very easy, I mean, nowadays. So that just try different combinations, 4, 5, 8, etc., and see which one is bigger, which one is faster. So that's called empirical search, and it's very popular. But the prerequisite is empirical search. It means that we need to have candidates. So it means that we have, next slide, please. So and next slide, please. So it means that we need to write not just this code once, but we need to write several versions of this code with different unrolling factors. So it means we have to keep write and rewrite such code. Next slide, please. Also, this program is called DUXP, D for double precision. And there's also SUXP, it's for single precision. There is CUXP for complex. So you need to do all these things for, for different variations of SUXP, and unrolling factors for single precision and complex would be probably different. Well, actually, they are different. And then in 2 years' time, Intel releases a new CPU, and you have to do this all over again. So as you can see that writing, such code and keep writing and rewriting an interval, it's become very boring, and some automation is actually needed. Next slide, please. It's very desirable. So the next question is, why not to use the compiler? Then, well, the reason is that although there are several compilers that produce CLLVM or WASM, for example, but they often need, or not always, often need a specific runtime. But the bigger reasons that a general purpose optimizing compiler is very hard to design. It takes a lot of resources. And therefore, given limited resources, it supports only the most profitable optimizations, which would be beneficial to most of the people. And it doesn't, therefore, the domain-specific optimizations are rarely at all supported. And by the way, even this optimization, like 0 multiplied by x, can be replaced by 0, where 0 is a floating point, is not optimization supported by optimizing compilers, because it's generally invalid. So it's not just profitable. It's generally invalid. It's only valid in some domain-specific circumstances. Next slide, please. And next slide, please. Okay. So for this reason, the domain-specific code generation has become widespread on high-performance computing. And here is a few names: Atlas, FFTW, Spiral, Halid, Firedrake. Well, probably some people heard of FFTW. And I point out only Halid. So you probably haven't heard the name. But if you own a smartphone, then you use Halid-generated code every time that you take a picture. And most of these libraries are generating C. So the target language is C. So it's all about generating C. So next slide, please. So let's, well, generating C is kind of the last, it seems to be, should be very easy, just generating strings. Okay, so let's take a look at one of the generators, Atlas, which is the state-of-the-art generating of basic linear algebra routines. Next slide, please. So this is the small fragment, and I mean small because the total size of the generator is about 3,500 lines. So this is a generator for matrix-matrix multiplication. So the first question is, if this code is even well-formed. Well, it looks like it generates some kind of assignment statements. Yeah, it looks like it's more or less well-formed, but there is a if statement and for loops. So maybe, how the code repeated is not clear that the overall code will be well-formed. But look at the variables, how the variables generated. So there is looks like there is a RC, which is the name variables, and I and J is some kind of numbers, and the variable name, the full name, is built by combining those pieces of information. Can you tell that this variable will be actually is declared in scope, and it is declared with the right type? Well, I mean, I don't know, who knows, because this declaration would be in some different part of the generator. It's not clear that, I mean, I don't know, all variables that are used will be declared. And as a matter of fact, the developers himself are on record for being frustrated. One can say, well, maybe this, I mean, well, okay, that, I mean, we can't tell if the code is well formed or not, and if variables are declared, but what's the big deal? So if you generated the code which is not well formed or well typed and with undefined variables, well, eventually compile the code and see the problem right away. As a matter of fact, I myself heard exactly such comment, and I have a good quote for you. Next slide, please. So the quote comes from this paper at Scala Symposium 2016. So this says, while we were able to resolve performance issues, we introduced new bugs. Well, how funny how often that happens. That would manifest the errors like that. Val x1343 equal x1232, and 10 probably other variables also named with x. Note that variables are indexed in ascending order starting at 0, meaning that a large piece of code is processed before we hit this error. And the error is that there are some variable, it's called there, the error message is issued by Scala compiler. It's compiling Scala, not C, but I mean, you can see the code is very, I mean, low level. There is some variable turns out to be not declared. As the author writes, the root cause of bugs such as this often proved to be very simple, but heavily obfuscated in the code it manifested in. Well, you can say that. I mean, I don't know. You can say that. So, and finding what's, I mean, where in the generator caused this problem, it proved to be very, very non-trivial. So next, please. Next slide, please. So we see that it's better to generate C code not in printf statements, but it's better through some kind of level of abstraction, and let that level of abstraction hopefully enforces some correctness assurances. So which assurances it enforces? Actually hard to, it's an engineering compromise because, well, of course we wanted to get full correctness, but it's hard to get. So, but at least we wanted to assure that generated code has no unbound variables, so it's type correct and compiles without errors and warnings. Next slide, please. So, if we generate abstract syntax tree, then and pretty print at the end, then well-formedness can be assured, but well-typedness and absence of unbound variables, of course, cannot. But in the paper, produces describes two methods that ensures all these guarantees. Okay, next slide, please. Next slide, please. So, as I just said. So, next slide, please. And the next one. So the name, because we are generating C from a high-order language, high-order, high-level language, then we're talking about heterogeneous metaprogramming. And there are two methods that they explicitly generate heterogeneous. It means embedding C in a host language as DSL, and implicitly. So I'll be talking about the last one, offshoring. Next slide, please. As a matter of fact, the paper also describes the first approach in embedding in a tagless-final style. Next slide, please. So here's the main motivating example. There is a OCaml code and C code, and you can see from the code what it does. Hopefully very easily, it just adds two vectors, which is a simple variant of the previous problem of Duxby. And the code is really so, well, of course, there are syntactic differences, but the code is so similar that, next slide, please. So it's tempting to think of this as exactly the same single piece of code, the same code, but just written in two different syntaxes. So a subset of OCaml can be seen as a different notation for C. Next slide, please. So here's the idea of offshoring. So if we can generate code in a host language, well, in OCaml, for example, with correctness guarantees, and if we can translate the generated host code into C, preserving the guarantees, then we attain our goal of C generation with correctness guarantees. So next slide, please. So the first point is how to generate, is the problem of homogeneous programming. So and quite a few languages nowadays, for example, C, OCaml, Haskell, F#, etc., have metaprogramming facilities. In this research, we use MetaOCaml, so generating OCaml code in OCaml dialog that generates OCaml code. Next slide, please. So the second if we just described before, and so offshoring is I mean, now we have both pieces of both conditions are satisfied, and so we can implement offshoring, which is implicitly heterogeneous programming. Next slide, please. So in a sense, it turns homogeneous programming into heterogeneous programming. And the key idea, well, how does it differ from compiler that we said before is not acceptable, because the code that we translate is not the full host language. It's only a subset of the whole language. And it's typically a very small imperative subset, which is much easier to translate than the whole language. Next slide, please. So next slide, please. So, of course, this is a very attractive idea, but as they say, the devil is in the details, and there are very many details. So one of them is, if we look more carefully at these two pieces of code, they are not as similar as initially thought, because C code has types, int and star, etc., but OCaml doesn't. So it means that we actually need to have type inference. Next slide, please. More challenging is extensibility. For example, C has a huge variety of int and float types, and more is added with each release of C. And many of them have no representation in OCaml. And also, when we wanted to generate code that calls C library function and uses their data types, and their data types might not be representable in a host language. And then another challenge is control structures of like for loops, do while, break, continuous, and go-tos, which I mean, not at all representable in OCaml. And of course, there are pointers and mutable variables. The paper describes all of those challenges, but I looked. I have very little time, but briefly look at the last one. Next slide, please. So if we write let x equal y in foo x, then it seems to be easy how to translate it and see what would be the image in C. Next slide, please. But because we're generating imperative code, then we need to deal with references. Of course, in OCaml, it's done in this way. And of course, it's easy to see how to translate in C. So now in translation, when OCaml has explicit reference operator, which is bang, we just remove it when we translate it to C, because the referencing of variables in C is implicit. Next slide, please. And now we get on the right-hand side OCaml code, and what should be the image of how to translate it in C. If you think it's translated in C how it's written on the slide, then it's not a very good idea, because the code has a very different semantics. So the paper talks about this in some details. So what's the problem with this? Next slide, please. So C variables, once you start generating it, you realize that C variables are very, very subtle. Next slide, please. And also C also has a reference types and the variables of reference types. So the complexity increases. Next slide, please. So the unsettling conclusion that OCaml isn't a good notation for C after all. Next slide, please. But the good idea is that OCaml isn't a good notation for the whole C after all. But C is redundant as many languages. So there are many ways of saying the same things. And it turns out, for example, the subset that we need for, like, for example, OpenBLAS is only very small subset of C, which is much more regular. And we can avoid all these words of C. And the paper talks a little bit about it. So next slide, please. Next slide, please. And as last, so the paper talks about not in more details about the offshoring and also about the first approach of embedding C in OCaml as a DSL. It has many examples, and it's written as a sort of FAQ. So how to do so and do so and so and so things with offshoring. And this FAQ came from the real experience. So when the students, most of the students or interns tried to use offshoring and they had questions, and the paper was actually written as an answer to all these questions that they got. And there are several applications using actually superset of C, generating not just C, but superset of C, like OpenMP, OpenCL, and subset of C, like the C dialect used for robot control code. And the approach that I haven't talked about, it's being used to generate FM radio applications from high-level description. And there is a code. The whole code is available at the companies of the paper. Okay, thank you very much. Thank you.